Alright, today I'm going to cover physics. This is paper 3, the core theory paper for May-June 2016. That's code 0625-31 and this is for the Cambridge International Examinations. Let's begin it now.
Hey Anna, on 3.
Okay.
1.
Tell me when. I'm ready to go.
2.
I was born ready. Yes.
Calm down.
Right, question 1. Figure 1.1 shows part of the speed time graphs for a cyclist and for a runner. Compare the motion of the cyclist and the runner during the first 6 seconds and explain your answer. Alright, let's look at the graph again and do a quick run through of it. Okay, so we can see there's a big gradient running up to that 6-second mark here, which is what we're really interested in. So let's just come down here. There we go. That's it. That whole section there, that's up to 6 seconds. We can see that both of them have got a gradient. What that means is that both of them are accelerating. And that's because acceleration is just change in speed divided by change in time. So because the speed's changing and the time's changing, we know they're accelerating. Okay, so acceleration, change in speed divided by change in time. I mean, technically, of course, change in velocity divided by change in time. But if the speed is changing, there's definitely an acceleration. Okay, so both the cyclist and the runner are accelerating. The cyclist has a steeper gradient, which means that it's accelerating at a greater rate. So let's write that down. As we saw, the cyclist has a steeper gradient. And what we said is that means that the cyclist is accelerating at a greater rate. So there we go. 3-mark question, 3 main points we've brought up. B. Describe the motion of the cyclist between time t is 6 seconds and t is 12. And what we can see is that the speed there is 9 meters per second and it doesn't change. So for describing the motion of the cyclist, we'd say that they're moving with a constant speed. There we go, moving with a constant speed. And part C, calculate the total distance travelled by the cyclist between time t equals 0 and t equals 12 seconds. Ooh, a little bit more interesting this bit. So what makes it interesting? Well, the distance travelled is equal to the area under the graph for a speed time graph. So this would be area A, this first triangle here. And this bit over here would be area B. So what I'm looking for is the value of area A plus area B. The distance travelled is the area under the graph, it's area A plus area B. And that is, of course, the area of the triangle plus the area of the rectangle. It's 1/2 times 6 times 9 for our triangle. Plus 6 times 9 for our rectangle. Which gives us 27 meters plus 54 meters, which is 81 meters. The unit's already down now, so 81 meters. There we go. And part D, after 6 seconds, the runner moves at a constant speed for 4 seconds. He then slows down uniformly and stops in a further 2 seconds. On figure 1.1, complete the graph for the runner's motion. So slows down uniformly just means slows down at a constant rate, slows down the constant acceleration. It really means a straight line. And he's going to slow down to a stop in 2 seconds. Okay, so moving at a constant speed for 4 seconds and then slowing down in 2 seconds. Slowing down to a stop. Let's put that into our graph. There we are. So we know that our runner runs with a constant speed for 4 seconds and then slows down to a stop in the next 2 seconds at a constant rate. There we go. Beautiful. Question 2. A boy steps off a high board into a swimming pool. Figure 2.1 shows the forces acting on the boy at one point in his fall. The 540 Newton force is caused by gravitational attraction, so it's this weight. State the cause of the 100 Newton force. Okay, so we get 540 newtons downwards, 100 newtons upwards, resisting the force. That is the force of air resistance. Alright, so that's 100 newtons is a force due to air resistance, and that's a lot of air resistance. So you'd have to be travelling at a very high speed to get that level of air resistance, given that he's pointing feet first and not belly flopping into the water. So I'm not sure how high that board is, possibly the height of a medium-sized building, or, whether that's actually air he's falling through. Part B, calculate the mass of the boy. Well, let's see. We know our equation for weight. Weight equals mass times gravity. We want to find the mass, so we just cover it over. And that leaves us with the equation we need. Mass equals weight divided by gravity, which of course gives us 540 newtons, divided by our value for gravity, which is, if you are ever unsure which value to use, go to the front of the exam paper. Here we go. Because in the front of the exam paper, it will tell you the value it wants you to use for gravity. So you might look at that and say, oh, I know gravity is not 10, I know it's 9.81. Be prepared to lose marks if you use 9.81. They're telling you the value they want you to use. They want you to use 10. And if they want you to use the value of 10, then 10 is what you should use. And that will give us a value of 54 kilograms. So 54 kilograms. Calculate the resultant force on the boy, state its direction. Well, what we have is 540 newtons down. We have 100 newtons up, which will give us a resultant force of 540 minus 100, which is 440 newtons. And the direction is down. There we go. Question number 3. Figure 3.1 shows a metal plate warmer. The plate warmer contains 2 small candle heaters. Plates of food are placed on top of the warming tray. State the process by which the thermal energy from the candles passes to the warming tray. Well, there's 2 ways it will pass. One is through radiation, from the heat being radiated, and the other one is through convection. So just pick one of them. I'll go with convection because it looks like they've tried to put a reasonable distance in between the candle and the plate being heated. But you'd also get a mark there if you put radiation as well. State the name of the process by which thermal energy moves through the warming tray. Alright, well, the way that heat energy moves through a solid is by conduction. It gets conducted through. B. The outside of the plate warmer is shiny. Suggest how this helps the plate warmer to stay hot. Okay, well, we know that shiny objects are bad emitters of radiation, thermal radiation. So there we are. Shiny surface is a poor radiator of heat. Part C. The handles of the plate warmer are made from metal. Identify a problem with this and suggest how the problem could be solved. Well, here's the problem. You're going to hurt your hands. You don't want metal plate holders, metal handles in a plate warmer. It's just going to burn your hands. So the handle will get hot. It doesn't have to get hot. It could just be uncomfortably warm. But there's no need for it. So the problem, the handles get hot due to conduction of heat. And the action, well, what can we do to solve that problem? We can cover the handles in some thermally insulating material. Question 4. Figure 4.1 is a simplified diagram of a geothermal power station. Describe the energy resource labelled X in figure 4.1. Well, it's a geothermal power station. It pumps the water down, the water gets hot, it heats up, turns into steam and drives a turbine. So the bit labelled X is the bit down the bottom. Well, that energy resource is going to be thermal energies, the hot section under the surface of the Earth. So the energy resource, thermal energy. B. Identify the useful energy transformation that takes place in the geothermal power station. Tick one box in each column. Input energy, well, the thing you're going to take the energy from is heat energy, isn't it? It's the thermal energy of the ground that they're sucking out. And the output energy, well, it's a geothermal power station. If all goes well, what you're going to get is electrical energy. There we go. Part C. State 2 disadvantages of obtaining energy from fossil fuels. Well, 1, atmospheric pollution. And 2, well, this is obtaining energy from fossil fuels, so these are non-renewable. That's our key point. What they've done here, always good to be aware of this, they've shown you an image of a geothermal power station. They've talked about geothermal power stations, and then they're asking you about disadvantages of something different. So always be careful when you read the questions. Don't fall into these traps that occasionally get put in, just to make sure you're paying attention. Right, question 5. Figure 5.1 shows 2 men repairing a weak roof using a crawler board. A. Explain why the use of the crawler board prevents the men from falling through the roof. Okay, well, first of all, let's deal with the issue. There are people out there who, when you say the roof is weak, it is not strong, are prepared to go up there with a bit of wood, stand on top of the weak roof and fix it. That's terrifying. They're pretty awesome people. Okay, let's look at that then. Pressure equals force over area. Now, why is a crawler board useful? Well, what happens with a crawler board, we're not just using feet anymore. Feet have a small area. That's a much wider area because of the crawler board. So the area gets bigger, force remains the same, or doesn't increase by much with the crawler board, and then the pressure will get smaller. So now we want to write that down. So we've got a larger area used to support the workers. What effect does that have? It will reduce the pressure beneath the workers. So there we go. We will reduce the pressure beneath the workers on the surface of the roof. B. The crawler board has a weight of 400 newtons. The total weight of the 2 men is 1600 newtons. The area of the crawler board is in contact with the roof is 0.8 meters squared. Calculate the pressure on the roof when the men are on the crawler board, including the unit. Okay, let's look at this. We're being asked to calculate the pressure. The first thing we want to do is write down our equation for pressure. Pressure equals force over area. So let's look at the force acting on it. We have 1600 newtons plus 400 newtons, the weight of the 2 men plus the weight of the board, and the area we're given is 0.8 meters squared. So that's going to give us 2000 newtons divided by 0.8 meters squared, which is 2500 newtons per meter squared. Now, those of you familiar with pressure know that pressure is measured in pascals. That's the unit for pressure. But a pascal is just 1 pascal is 1 newton per meter squared. I've left the units like this in the calculation just so you can see where they come from. You've got newtons here divided by meters squared. What happens when you get newtons divided by meters squared? Nobody knows. So if you just leave the units there, you can see where the number itself comes from. And that gives you a lot of information about the number itself. So newtons meters to the -2 is just leaving the units in there, but I could just as easily write pascals because 1 pascal is 1 newton per meter squared. That's a key part about physics. Physics isn't about the accuracy of the answers as much as it's about communicating the information. Question 6. Figure 6.1 shows an experiment to observe the motion of smoke particles in air. We've got a little Brownian motion experiment now. The light and smoke particles in a microscope, and we've got a bright dot. Figure 6.2 shows the view through the microscope of one smoke particle, labelled P. On figure 6.2, draw 3 lines to show the movement of this particle. Now you might be tempted to take the smoke particle and say, it does this. But a couple of things. One, it's asking you to draw 3 lines to show the movement of the particle. here. So it only wants 3 lines. And 2, there are things that I've drawn here that it doesn't do. It doesn't move in a lovely curve. It moves in little jagged ways like that. So we want 3 lines, 3 straight lines. 1, 2, 3. Oops. 3. There we go. 3 straight lines showing the movement of the particle. A, part 2. Explain what causes the smoke particle to move. Well, it moves because of all the collisions between the air particles and the smoke particle. So collisions between the air particles and the smoke particle. And every time the air particle, or every time an air particle comes in and hits the smoke particle, then the smoke particle rebounds, it recoils, moves off in another direction in another straight line until it gets hit by yet another air particle. B. The air containing the smoke particles becomes warmer. Suggest how this changes the movement of the smoke particles. Well, it means that the air particles are going to be moving faster, so we're going to be hitting it more often, and that means that the particle will change direction more often. So there we go, the smoke particles will change direction more often. Question 7. Figure 7.1 shows equipment used to demonstrate thermal expansion. The copper rod is heated and expands. It turns the roller and moves the pointer. So figure 7.1, draw the new position of the pointer. So what's going to happen as it expands, it's going to stretch out in this direction, and this pointer is going to move this way. There we go. I'm going to just score that out because obviously I wouldn't want to leave that in an exam paper because it only wants me to draw one arrow. If I start drawing random ones in the middle of nowhere, I'd lose marks. B. As the rod is heated, some of its properties change. Identify how each property changes. Place 1 tick in each row of the table. Okay, well, first thing that I know is it's going to get longer, it's going to get wider, it's going to get thicker, just because it's being heated up and all the atoms of copper move further apart just slightly. So that'll have a series of effects. Let's look at what effects that could have. Right, the property of the rod. Well, the volume, here we go, the volume's going to increase, and that's going to increase because all the particles move further apart. Now we've got mass and density. Mass isn't going to change, it doesn't change at all. And density, well, density equals mass over volume. I know that the volume is getting bigger, which means the density will get smaller. So this one will decrease. Let's write that in. So the volume increases, mass stays the same, and density decreases. State one disadvantage of thermal expansion. No, I guess if you've ever seen train tracks, there are some pictures out there on the internet showing train tracks that have undergone thermal expansion, and they get all bent up and all buckled. Let's put that down. Train tracks can buckle. And that's why you get that characteristic sound when you're on that train, that da-da-da-da-da-da-da-da. That's because the train carriage that you're on is going over the little gaps, the little expansion gaps that they leave in between sections of track. So leave little gaps for them to expand into. Question 8. A student directs a ray of light towards a plane mirror, as shown in figure 8.1. Name the line labelled X. Well, that's at 90 degrees, that's our normal line. And 2. When angle A is 45 degrees, angle B is also 45 degrees. Alright, angle A is changed to 20 degrees. What is the new value of angle B? Well, if angle A is going to change to 20 degrees, here we go, it's going to come in like that. That's probably 15. Then angle B, here we go, oops, is also going to be 20 degrees because it's a mirror. So there we go, our first option, 20 degrees. Alright, B. And it looks like someone's decided to have fun. I think perhaps Somebody bought the person doing the examiner, someone must have bought them a geometry set. This is why you don't let children play with dangerous toys. Okay, let's look at it. See what they're going to do with this. Complete the table using the labels from figure 8.2. The first label is done for you. Angle of incidence, angle A. Okay, it's going to ask for refraction, reflected angle, critical angle, and a refracted ray. Alright, well, we can do this. It's not too bad. Start with the angle of refraction. Refraction happens when something changes speed. It changes speed and changes direction. In fact, that only happens in one place. It happens here. So the light ray has changed speed and it's changed direction. That's D. Now, an internally reflected angle. Okay. So internally reflected, but the top's talking about a mirror. So it's not there. It has to be somewhere inside the glass block, and it's internally reflected. And if you look at this, it's being reflected. There we go. It's being reflected at this point. That's the internal reflection. So the internally reflected angle is this one. The internally incident angle would be this one. The internally reflected angle would be, so this would be the incident angle, this is the reflected angle. Even though they should have the same value, it's going to want the correct one to be picked. So the internally reflected angle there should be G. Now we have to find the critical angle. And what we can see here, the critical angle is a bit where you can see this line is going down at that 90-degree angle. We got that's S. We got this line here, T. They're both being split from the line R. Now, the light will go at the critical angle. The light will travel along the surface of the block. And of course some of it's reflected back in. That's what we're seeing there. So this incident angle here is the critical angle. So that's F. And a refracted ray. Okay, well the ray being refracted, here we are. This is most likely A right here. This is, well, it's glass. There we are, so it's glass. It's being refracted as it travels in. This bit here, R, is our refracted ray. There we go. C. A student uses a converging lens to produce an image of an object. Figure 8.3 shows the arrangement. On figure 8.3, using a ruler, carefully draw two rays from the object O to locate the position of the image, using the arrow to represent the image. Alright. Well, the first line I'm going to draw straight through the centre of the lens and straight on. Second line I'm going to draw is through the focal point on the same side of the lens to the centre line, and then of course from there straight on. And there we go. So now all I have to do is draw the image of the object. And there we are, a thing of beauty. The only thing I'm going to do now is just label that image. And there we go, problem solved. Question 9. Figure 9.1 represents the regions of the electromagnetic spectrum. Part A. Complete figure 9.1, so add the label of the missing region. Alright. Well, what do we have? Short Gavin executes unwelcome visitors in a mad rage. So in is infrared. Two, complete the label under the arrow. You know what I could do? I like to just tick these off as I'm doing them. Complete the label under the arrow. Here we are. The arrow is this one. It's pointing to the right. And what we see is that is the increasing frequency. Increasing frequency because the energy is getting bigger and bigger. That's why gamma rays are so dangerous and so penetrating. They get very large amounts of energy. B1, state 2 uses of X-rays. Well, one looking for broken bones, I think is probably a really big one. And the other thing they're pretty handy for is treating cancer. You can use very intense X-ray bursts to kill off cells, kill off cancer cells. There we go. B2. Describe 2 safety precautions taken by people using X-rays. Alright, well, step 1, lead apron. If you've ever had one, I imagine many of you have, then you'll know that that's one of the things they put over you in areas they don't want exposed. So lead apron. And the other thing, well, there's a whole bunch of them actually. I think a key point is avoid when pregnant. There are other things that they do. The person using the machine might be in a different room when it gets used so they can limit their exposure. It's another key point. 3. X-rays and light waves can both travel through a vacuum. Identify the correct statement. Tick 1 box. X-rays travel at a slow speed and light waves? No. The same speed? Yes. In a vacuum they're going to be travelling at the same speed. Question 10. A student makes a circuit shown in figure 10.1 using a 12-volt battery. Complete the sentences about the circuit using words from the box. Okay, component X and Y are connected in series, one after the other. And component Y is a thermistor. Now, B. Figure 10.2 shows how the resistance of Y varies with temperature. Alright, as the temperature increases, the resistance decreases. It's not a straight line. Okay, so describe how the resistance of Y varies with temperature. Well, there we go. As the temperature increases, the resistance decreases. And the other thing you will notice about it is it's not a straight line, so it's not linear. There we go. Now, part 2. The temperature of Y is 10 degrees Celsius. The resistance of X is 20 ohms. Calculate the combined resistance of Y and X. So the total resistance is just R1 plus R2. And that's 20 ohms plus the resistance of our thermistor when it's at 10 degrees. So let's look at that. Let's go back to our graph. So when a thermistor is at 10 degrees, there we go, the resistance is 80 ohms. So that's the value we should be using. There we are, so the value of the resistance is 100 ohms. Now calculate the current in the circuit. Okay, we know that V equals IR. We want the current, VIR. We want to calculate the current, which is cover over current. There we go, and it's V over R. So I equals V over R. The voltage is the supply voltage, which is 12 volts. And the resistance, we just calculated out, is 100 ohms, which will give us 0.12 amps. There we are, 0.12 amps, and that's our answer. Let's go on to question 11. Question 11. Put a ring around the names of the materials which are attracted to magnets. Okay, let's look at those. Aluminium, no. Copper, no. Iron, yes. Mercury, no. Magnesium, no. Steel, yes. And tin, no. Figure 11.1 and 11.2 show magnetic field patterns for bar magnets. On each diagram, correctly label the poles right, north or south. Okay? So the first one's always going to come out of the north and into the south. North and south, and just to make sure, The other end we'll label with the opposite pole. C. For each diagram in figure 11.3, describe the force acting, if any, using words attraction, repulsion, or no force. Ooh, two positively charged spheres, they are going to repel each other. So repulsion. And two north poles next to each other, they are going to repel each other as well, repulsion. And a magnet and an uncharged plastic strip, no effect. What word do they want us to write for that? No force, okay. No force. Question 12. Two radioactive sources are used by a teacher. One source emits only alpha particles and the other source emits only beta particles. A. Suggest how the sources can be identified. Okay, so we've got one source which emits alpha particles and another one which emits beta particles. And it wants us to identify the sources. Best thing we can do, get a radiation detector and put a piece of paper in front of it. Because alpha particles cannot pass through the paper. So we use a radiation detector, place a piece of paper in front of it, and place the two sources one at a time next to the paper. And we know that alpha particles are stopped by paper, but beta particles are not. B. The teacher also has a source that emits gamma rays. State two ways in which gamma rays are different from alpha particles. Okay, well, gamma rays are... they're electromagnetic rays. So they're a wave. See, alpha particles are literally little particles. And two, but another way they're different. Gamma rays are not stopped by a piece of paper, they're much more penetrating. So gamma rays are not stopped by a piece of paper, they're more penetrating. And C, state an effect of ionizing radiation on living things. Well, it damages cells, it can actually damage DNA, it causes cancer. This is one of those things that gets brought up quite a lot, the effect of ionizing radiation, so it's good to know them. It damages the cells. There we go. That's it. That is the end of that paper. So I hope you've enjoyed it. Hope that's been useful for you. If you liked it, then please feel free to like and subscribe. If you've got any other requests for me to run through, then please feel free to leave a comment below. Either way, have a great day.